In our last video, we integrated a definite integral using its definition, but to do so I had to tell you that that function was integrable so that we could choose a particular partition. We'd subdivide the x-axis into intervals of equal width, and we could use the right-hand endpoints that we're comfortable with. This theorem is how I knew that function was continuous. The integrand from the previous video is x squared plus x, which I know is a continuous function. This theorem says if f of x is continuous on the finite closed interval ab, or has at most finitely many jump discontinuities on that interval, then f of x is integrable on that finite closed interval ab. That is, the definite integral exists. Definite integral exists, and then I know I can use whatever partition I want. One of the ideas in the proof of this particular theorem is that if I have a continuous function and I divide up my x-axis, no matter how I divide up my x-axis, each subinterval is a finite closed interval. Well, a continuous function over a finite closed interval has to achieve both an absolute maximum and an absolute minimum, which means I could find a rectangle that would belong to an upper sum approximation and a rectangle that would belong to a lower sum approximation. As I take the limit as n approaches infinity of the upper and lower sums, they would have to get closer and closer together, sandwiching the true value of my definite integral in the middle. I'm allowed to have finitely many jump discontinuities because then I could repeat the process on each piece between jumps and just add those numbers together. This theorem comes in handy when we're looking to see if a function is integrable or not. If I have a continuous function or a piecewise continuous function with finitely many pieces, then I know the definite integral will exist. That brings us to a theorem that applies anytime I have two functions, both of which are integrable over the closed interval ab. To start off, we have what's known as the order of integration property. And so what I want to think about now is, instead of writing my definite integral from a to b, what if I swap the order of the bounds? Right? What if I integrated from b to a? Well, if I think about the picture I'm used to drawing, it's like instead of thinking about things going this way, we're thinking about things going that way. And I bet you can actually guess what would happen to the value of the definite integral when I swap directions. We get the opposite of what we started with. In mathematics, oftentimes when you change direction, that's associated with a minus sign. The way I like to think about this is that if I'm thinking about delta x, and I'm thinking about delta x in the case where I have equal width subintervals, this delta x would be b minus a over n. Well, this one would be a minus b over n. They have opposite signs. So when I change directions, if I switch the order of integration, I change the sign on my definite integral. The zero width property says that if I integrate from a to a of f of x dx, I get 0. Well, I like to visualize this one as having a function and trying to integrate starting and stopping in the same spot. Well, that's just a vertical line. I wouldn't even get a rectangle that has area 0. So order of integration in the zero width property. Next, we have the constant multiple rule, which says if k is a constant and I try to integrate from a to b k times f of x dx, then I get the same thing as if I multiply the definite integral by k. I get k times that definite integral. Well, if I think about the definition of the definite integral, the limit as n approaches infinity of the Riemann sums. And then I was to imagine multiplying the function by a constant k, well, that would just make this times k. All my y values get multiplied by k. Well, this is a sum, and sums have a constant multiple rule, which says I can factor that k out front of the sum. And then I see that this is a limit, and limits also have a constant multiple rule, which says I can bring that constant all the way out front. And that's why I'm allowed to bring the constant out front of my definite integral. All right, my sum/difference rule is my first rule that I need two functions to think about, f of x plus or minus g of x. Well, I get exactly what you'd want to get. That I can compute the two definite integrals and then just add or subtract them based on whether I was adding or subtracting before. And one way to think about this is both the sums have an addition rule that looks like this and limits have an addition rule that look like this, so I can just apply both of them. All right, this is going to sound odd, but additivity is my favorite rule about the definite integral. The integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b. Okay, so what this says, I can integrate from a to c and then integrate from c to b, and if I add those together, I get what I would have gotten if I just integrated from a to b. Now, I like to think about that in terms of a picture. Let's say I just have a well-behaved function. And then maybe I think of a value c. This area would correspond to the notion of the definite integral from a to c of f of x dx. This shaded area would correspond to the area from c to b. And if I add the red and blue areas together, well, I would get the total area. And I know the total area is the definite integral from a to b of f of x dx. And that's additivity. Now, that said, my rule for additivity did not say that c had to be between a and b. And that's kind of the best part. It doesn't. The rule for additivity works for any values a, b, and c, so long as my function is integrable over the largest finite closed interval. So let's imagine now I had this situation. Where now I'm not just integrating from a to b with c in the middle. It looks like c is larger than b. So the integral from a to b of f of x dx would be that shaded region. The integral from b to c would be the area of that shaded region. And then the total area, which I don't want to shade all in because I want to still see what I've shaded in red and blue separately, would be what the area I've traced in purple. And so the whole thing, well, let's just talk about the integral from a to b. Well, this is too much, but it's too much by exactly that amount. So I could take the integral from a to c, take away the integral from b to c. And now, if I just apply my very first rule, order of integration, I swap the order on this second one. Instead of from b to c, I would go from c to b, and instead of subtracting, well, I'd have to add. Well, that would be the integral from a to b of f of x dx. So additivity works for any three numbers and doesn't depend on the order. Two more properties to go. We have the min-max inequality and what is referred to in your textbook as the domination inequality. So the min-max inequality says this. The minimum value of f times b minus a is less than or equal to the definite integral from a to b of f of x dx, which is in turn less than or equal to the maximum value of f times b minus a. Well, this one is almost silly. If I draw a function that's integrable, and this one assuredly is, I will shade in green the definite integral. The minimum value of f, clearly right here. Well, that height times b minus a would be the area of this rectangle, which is very clearly less than what I shaded under the function. One way I like to think about this is the one rectangle lower sum. Well, the maximum value of f right here times b minus a would be the area of this much larger rectangle, which would be the one rectangle upper sum. Well, the true definite integral is definitely between those two values. All right, and for our final property of the definite integral, if f of x is always bigger than or equal to g of x on the interval a, b, then the definite integral from a to b of f of x is greater than or equal to the definite integral from a to b of g of x. And there are those 7 properties. In my next video, we're going to do an example that incorporates some of these ideas.